Now let us understand the one topic here, small topic here. That is again antenna aperture here. Oh, okay. Now let us consider the receiving antenna here, which is a rectangular horn electromagnetic antenna here. Rectangular electromagnetic horn here. Okay, this is how the rectangular horn antenna is there here, which is immersed in the whatever the uniform plane field is there, as shown in the figure here. You can see this is what is our antenna here. Side wall is there here. Okay, these are the side walls here, and this is what is the arrow mark which is pointing towards the up here. That is nothing but a electric field at the mouth of the horn antenna here. It is horn rectangular antenna here. That is AP is nothing but here. Whatever the physical aperture we are having for that particular uh, antenna here, that is nothing but a physical uh, the surface that is available here. Mouth of the horn rectangular antenna here. Right? And what about this one here? That is the direction of propagation of plane wave here. That is represented okay, as it is a receiving antenna. No, it should be the arrow should be pointing towards the mouth of the receiving antenna here. That E is the thing whatever the field we are having here. Okay, let the power density of the particular plane wave be S watts per square meter here. Whatever the plane wave which is going to be traveling towards the mouth of the rectangular horn here will be having the power density as capital S here, which will be represented as watts per square meter here. And whatever the area is there, no, or the physical aperture of the horn, whatever the physical aperture is there, the mouth of the horn rectangular here, that will be represented by AP square meters here, length into breadth here. Okay, that's why square meters. If the horn, whatever the horn is there here, okay, if it going to extract all the power here, all the power, okay, from the wave here over its entire physical aperture here, and the total power absorbed by from the wave is equal to P is equal to E square divided by Z into AP here. Okay, this could also be written here, right? How much power that has been absorbed by the physical aperture of the particular horn rectangular antenna when a wave is being going to be incident here, right? So P is equal to E square. E square is nothing but energy divided by whatever the resistance we are having, that is impedance Z into whatever the physical area we are having. That's what is represented S into AP. Also, it is correct here. S is nothing but here power density here. Right. Now, the total power it extracts from passing wave here, which is proportional to the aperture here. Okay. Now, but the field response of the horn is not uniform here. Remember, whatever the response we are getting from the physical area of the horn antenna may not be uniform here. Okay, so that's why whatever the electric fields at the side walls are there, no, that must be equal to 0 here. Thus, the effective aperture AE, now see here, effective aperture, the horn is always less than the physical aperture of the given antenna here. So that's why aperture efficiency is given by, okay, efficiency AP is equal to AE divided by AP here. Okay, AE divided by AF, AP here. AE is the thing which is effective aperture. How much the part of the particular rectangular horn antenna is able to absorb the power from the wave here. How much area? It is effective aperture here. Okay, physical aperture is whatever the area of the particular antenna is available here, right? Okay, this is how the antenna, aperture efficiency could be calculated here. Okay, AE divided by AP here. Now let us try to understand the relationship between the directivity and whatever the effective aperture of an antenna is there here, right? So this is again the effective aperture, or you can say effective area of the particular antenna here. That is represented by AE here. The arrow mark which is pointing towards the upward is the temperature electric field at a aperture A here. Okay, and this is how the conical shape here, beam array here. Okay, and this is what is the distance R from the beam array here, and this is how the electric field, okay, which is pointing towards upward here for the R here at a distance R. Okay, now consider an antenna here with an effective aperture AE, which radiates all of its power in a conical pattern of beam area as shown in the figure. Assuming a uniform field here, A is nothing but here uniform field over the aperture here, then how much the power it is going to be radiated? You know, P is equal to E square divided by Z naught into whatever the effective aperture we are having here. Z naught is nothing but here impedance or characteristic impedance we can consider. So that's why equation number 1. Okay, now intrinsic impedance of the medium it has been given already. Now assuming the uniform field ER in the far field here, remember far field at a distance R here, then how much power that is will be radiated here? That is equal to P is equal to whatever the field, electric field ER we are having here, to the whatever the impedance we are having, and what is the distance here, R square into whatever the beam area we are having here. Right? This is how the power radiated could be written here at a far distance R, okay, which is again uniform field through the beam area, would be written as ER square into R square beam area divided by Z dot here. So we know that here whatever the electric field at a far distance is equal to whatever the electric field of a particular aperture effective divided by the distance into the wavelength here. So we know that this is equation, standard equations we are having here. That is here is equal to EA into capital EE divided by R into H here. So using this particular formula here, we can write what we can write here is P is equal to power P is equal to substituting the value of ER here in the equation number 2 here. What we get here is P is equal to whatever EA square EE square divided by R square into lambda square into Z naught. Okay. R square into whatever we are having as a V meter here. Then R square get cancelled. So what's remaining here? Whatever the electric field, uniform electric field at aperture A, and the effective aperture is the lambda square Z naught into whatever the beam area here. Equating equation number 2 and 1 here. We have, so 2 is nothing but here, sorry, 1 is nothing but here. Whatever mm, the power radiated at the power radiated to, which is the uniform field EA for the aperture here. So that power and whatever the power we are having at the present here. Okay, so E into E divided by lambda square into whatever the Z naught into beam area. Okay, we are getting E square is into EE divided by Z naught here. So if at all we cancel out the common terms here, the Z naught get cancelled, and whatever the E square is get cancelled here. So one E will be getting cancelled in the LHS here comparable to the LHS here. So at the end what we're having here is effective aperture into whatever the beam area we are having here is equal to lambda square here. Okay. Now effect aperture beam area radiation here. Okay. Okay. Now beam area is equal to uh, now we already know that the directivity in terms of the beam area can be written as directivity D is equal to 4 pi divided by whatever the beam area is there. So beam area is represented with the 4 pi by D here. That equation can be written in lambda square is equal to AE into 4 pi divided by D here. So D lastly could be written as 4 pi divided by lambda square EE. Okay, this is how the directivity, or you can say that relationship between the directivity and the effective approach of an antenna could be found out here. Okay, like this we are having around another two derivations here. Okay, for isotropic antenna we all know that the directivity is equal to 1 here. Mm, that means here we are going to generate the radiation in all the directions equally here. So then the effective aperture is given as E is equal to D into lambda square divided by 4 pi here. If at all like if D is equal to 1 here, then we will be having A is equal to 0.0796 into whatever the lambda square we are having here. Okay, this is how we can understand regarding the antenna basics here, and further I'm going to do the further topics in the second video here. Okay, if you have any doubts here, please let me know here. Okay, please ping me in the WhatsApp or just send me a mail here, but all you are not able to understand here. Okay, just we'll have a revision up to whatever we have done here. We try to define the first, or you can say we try to introduce regarding what is exactly the antenna and what is exactly the isotropic and non-anisotropic antenna. What are the selection parameters we require here, and also what are the key factors in identifying the transmitting and receiving antenna here. Thereafter, we try to understand this equation of radiation here, then trying to understand regarding the transmitting antenna and receiving antenna diagram here, how exactly it is going to function here. Thereafter, we try to understand regarding the pattern here. Okay, that's nothing but here main beam, minor beam. Okay, okay, and whatever the field pattern is there in terms of the back lobes or the side lobes or whatever the main beam is there. We try to understand again null also here where there is no radiation here generated. Then we are having these three patterns here. Thereafter, we try to understand the beam area here. Okay, so we are having certain definitions concerning the beam area here. Thereafter, we try to understand regarding the beam area formulas here. Okay, beam area is a solid angle here through which all of the power is being radiated by a particular antenna would stream out here if the power maintained is maximum value here over the beam area, and also elsewhere is equal to 0. Okay, that is what is the definition of the beam area here. Thereafter, we try to understand the radiation intensity here, and we try to understand again the beam efficiency here, and also stray factor, directivity, gain, and we try to understand regarding the antenna aperture here. And after that, we try to understand regarding the relationship between the directivity and the effective aperture of the particular antenna here. If at all you have any doubts here, please ping me. Okay, we'll be stopping at this point here. Further topics will be in the next video. Thank you.